Hello, my name is Mohammad Amin Choursai. Today I'm presenting the paper on the compressibility of affinely singular random vectors for ISIT 2020. I was affiliated with Sharif University of Technology when I worked on this paper. This paper is a joint work with Arash Amini in Sharif University of Technology and Stefano Reni in National Chiaotong University. The compressibility measures based on the Shannon's entropy has been widely used in the area of information theory. As a brief introduction, the Shannon's entropy quantifies the minimum number of bits needed to transmit a discrete source. For a general probability measure, which is not necessarily discrete, the Reni information dimension as an abbreviation RID is introduced. The RID intuitively evaluates the ratio of the minimum bits needed to transmit X with high fidelity and the minimum bits needed to transmit any one-dimensional source with the same fidelity. Although the RID for absolutely continuous or discrete random vectors are already known, there are some questions which their answers are yet to be determined. As an instance, generally speaking, the value of RID for probability measures with singularity or the value of RID-based compressibility measures for stochastic processes with singularity is unknown. Also, the relationship between the RID and other compressibility measures are generally unknown. In this work, we consider a class of stochastic processes which are generated by passing a discrete continuous white noise from an FIR filter. The noise is called the excitation noise of the stochastic process. This class of processes is a subclass of moving average processes in which the excitation noise is with a general and not necessarily discrete continuous distribution. One can see that each sample of this type of process can be represented as a linear transformation of independent discrete continuous random variables. To find the compressibility of these processes, we define affinely singular random vectors and study their RID. Furthermore, we show that a linear transformation of orthogonally singular random vectors, which include a vector of independent discrete continuous random variables, can be represented as affinely singular random vectors. Using this argument, we then find the RID-based compressibility measures for moving average processes with discrete continuous excitation noise. Then we show that these compressibility measures are equal to the minimum epsilon achievable rate, which are known compressibility measures for stochastic processes. In the following slides, I first introduce the affinely singular random vectors and their associated probability measures and express their applications. Then I review their definition of RID for random variables and its extensions for stochastic processes. Next, I show the evaluation of RID for affinely singular random vectors. I talk about the equality of information dimension and epsilon achievable rates of discrete continuous moving average processes. And finally, I conclude the paper and talk about possible future research directions. The probability measure mu associated with a random vector is called singular if there exists a zero Lebesgue measure set S with non-zero probability measure mu. On the contrary, we refer to mu as an absolutely continuous measure if no such subset exists. As instances of singular measures, we have discrete measures which supported on a computable set and discrete continuous measures which are convex combination of a discrete and absolutely continuous measure in one dimension. Next, we studied affinely singular random vectors. An affinely singular random vector Zm takes the value of Z tilde I with a random chase V. Note that Z tilde I are isometric affine transformations of hi dimensional absolutely continuous random variables to Rn. Furthermore, we refer to Xn as an orthogonally singular random vector if its elements takes the value of xci and xdi with a random choice nu I. xdi's and xci's are elements of independent, discrete, and absolutely continuous random vectors, with the latter independent of nu as well. As an example, if we consider xdi's, xci's, and nu i's as mutually independent random variables, xn will be a random vector with independent, discrete, continuous random variables. Moreover, it can be shown that linear transformation of xn has singularities on affine subsets, or equivalently is an affinely singular random vector. As an application of these results, we consider an FIR filter which takes IID discrete continuous input and generate a process which we refer as discrete continuous moving average process. One can see that each example of this process is a linear transformation of IID discrete continuous random variables. Hence, using the results in the previous slide, one can see that the samples of this process form affinely singular random vectors. Now we review the definition of RID for random vectors. The random information dimension is the limit of the entropy of Xn, which uniformly quantized with step length 1/n over log m, as m tends to the infinity. Moreover, there are two known extensions on RID for discrete domain stochastic processes. The first of which is block average of information dimension for large blocks. This measure is only defined for stationary processes. The other definition, which is called information dimension rate, is the limit of entropy rate of quantized samples with step length 1/m over log m for large m's. Although this definition is not restricted to stationary processes, it is more complicated to evaluate since it is hard to find the entropy rate of quantized process for any step length. Now we get back to finding the RID of affinely singular random vectors. In the first lemma, we showed that the RID of a affinely singular random vector Zn, which takes hi dimensional singularities with random choice v, is the average of these dimensions over choices of v, provided that v is a finite entropy random variable. Using this result, we then prove that if xn is an orthogonally singular with random choice nu, and ym is a linear transformation of xn using the matrix A, the RID of ym is equal to the average rank of A nu over different choices of nu. Here A nu means the submatrix of A formed by columns for which the corresponding element of nu is 1. As an illustrative example, here we plotted the joint distribution of 3 independent Bernoulli Gaussian random variables. It means each dimension takes 0 with probability 0.5 and takes the output of a Gaussian random variable otherwise. The RID in this case is the sum of the RID in each element, hence equals to 1.5. There is a known result on RID which shows that an invertible matrix preserves the RID. Therefore, in here, the transformation of the random variables using A has the RID 1.5. But for a non-invertible matrix A tilde, we couldn't simply find the RID. However, our result shows that the RID is calculable and is equal to 11/8. Furthermore, as a side result in a lemma, we show that the maximum RID over n-dimensional Lipschitz functions of orthogonally singular random vectors is achievable using a matrix which its spark equals to its rank plus 1. Van der Moon matrices are special examples of these matrices. Next, using these properties of RID for affinely singular random vectors, in this paper, we show that both extensions of RID for a discrete continuous moving average process coincide on the marginal RID of the process excitation noise. Next, we move forward to find a relationship between the information dimension and minimum epsilon achievable rate for these processes. To do so, we first review the definition of minimum epsilon achievable rate. For a stochastic process xt, we call two functions fn and gn an epsilon encode-decode pair with rate rn if fn encodes n samples of the process in nRn dimensions, and gn reconstruct xn with error probability less than epsilon. Then the limit of the set of all such Rn's is called minimum epsilon achievable rate. If we do not deploy any further restrictions on Fn and Gn, the minimum epsilon achievable rate will be equal to 0. However, due to practical considerations such as complexity of encoder-decoder pair or noisy compression, we usually consider two regulations in which the encoder is linear or the decoder is Lipschitz. In the first case, we show the minimum epsilon achievable rate by R star of epsilon, while for the second, we use the notation R of epsilon. Then we prove in paper that for a stochastic process ZT with finely singular samples taking HI dimensional singularities with random choice Vm, the block average information dimension is equal to the average of HIs for various choices of Vm over M for large M's. Moreover, if we have a concentration inequality on the dimension of singularities, in the sense that there exists large enough M in which the ratio of the singularity and M is arbitrarily close to the BID with arbitrarily large probability, then we can say the minimum epsilon achievable rates for linear encoders and Lipschitz decoders both are equal to the BID. Fortunately, as we show in the paper, this is the case for the discrete continuous moving average processes with finite discrete sample space. Hence, we see that both minimum epsilon achievable rates are equal to the marginal RID of the process excitation noise. Finally, we show that the noisy undersampling can be reconstructed using a known algorithm named Lagrangian MEP. As a summary, in this work, we introduced affinely singular probability measures as a probabilistic structure for compressible random vectors. Using this structure, we represent linear mappings of orthogonally singular random vectors, including a set of independent discrete continuous random variables. Then we find the RID of these random vectors. Deploying these results in discrete continuous moving average processes, we show that their information dimension coincide the RID of marginal distribution of their excitation noise. Then we show for a class of processes with a special type of concentration on singularity dimensions. We have minimum epsilon achievable rate equal to the BID. Next, we show that a subclass of discrete continuous processes satisfies this concentration. As a side result, we show that some type of matrices maximizes the RID of functions of orthogonally singular random vectors for any n-dimensional Lipschitz functions. Furthermore, you can find the evaluation of another compressibility measure of affinely singular random vectors in the full version paper. As a future research directions, one can study the information dimension of continuous domain processes with such compressible structures. The evaluation of BID and IDR of other discrete domain processes, including non-stationary processes with such singular realizations, would also be interesting. Thank you.